Swayam Prabha. Digital India. Educated India.
Hello and welcome everyone to this lecture series on the modeling of multiphysics system. So, this series we had divided into 3 segments, and based on which we have been going over initially on the concepts of mathematics. So, those were our mathematical preliminaries. So, in that segment we had covered concepts like the summation notation, vector calculus. We had looked at how to non-dimensionalize an equation, what is the effect of non-dimensionalization, why is it important. Then we have also gone to some extent in depth into numerical methods and how we can apply them to the governing equation of physics. In the second segment, and that is what we have been covering over the majority of the last set of lectures, which we have talked about single physics models. So, in depth we have gone into the modeling aspects for heat transfer, mass transfer, that is transport phenomena. We have gone into solid mechanics and seen how stresses and strains behave, how the Navier's equation comes up, and then different methods to apply to get displacement, stresses and strains. Then we have gone through fluid dynamics, electromagnetism and electrochemistry. So, these models of single physics we have done both in terms of analytical solutions as well as from a numerical perspective, and seen that how these equations would behave. Single physics modeling was important, so that we have a strong fundamental understanding of how individual physics would behave, and without the interference of the other physical phenomena, right. However, most of the physical applications, as we have seen in our introduction slides, are a composition of several physical phenomena together. Heat transfer does not act alone. Heat transfer can also cause an expansion of a solid or an expansion of a gas. Expansion of a solid is a solid mechanics problem, and therefore, we can couple the two together, and that's called thermoelasticity. Likewise, temperature differences can cause changes in the density of a fluid. Fluid densities can cause flow, and that is convection, and convection therefore, is a combination of fluid dynamics and heat transfer. Likewise, we have an electromagnetism coupled with heat transfer, that is electric resistive heating and so on. So, most of these examples are a combination of multiphysics, and from this lecture onwards in the upcoming set of lectures, we will talk about several multiphysics systems using our understanding and concepts of single physics equations. We will try to couple the equations together, in which the variables like temperature will be coupled with stresses, and stresses will be coupled with temperature or displacement, and we will finally have a set of analysis methods which we will be able to adopt and apply. These will be both numerical and analytical, so that we can decouple these equations or solve them in a coupled format and get a set of solutions. All right. So, with this introduction, we will start our set of lectures on these multiphysics systems with thermomechanical systems. So, this is the first lecture on the thermomechanical system, and we will go into the introduction. So, a thermomechanical system is a system that couples heat transfer or thermal gradients as an input into an elastic response or a solid mechanical response in the terms of displacement or stresses as an output, right. So, a system that takes a thermal input and gives a mechanical output is a thermomechanical system. Right. So, in all of these systems we are giving in heat in some format, either directly to a solid structure or via a medium, and that heat is getting converted into stress or in terms of deformation in some way, and that deformation is our response, is our output. And therefore, such systems are majorly used in many of the actuating devices in MEMS and NEMS application. For those who do not know what MEMS and NEMS are, that is micro electromechanical systems and nano electromechanical systems, right. So, for example, we can take a classic Feynman's example. So, it's called a Feynman heat engine, or a Feynman's design of a simple heat engine, right. So, this is a wheel with spokes made of elastic bands or rubber bands. The wheel is heated from one end, causing a shift in the center of mass, due to the contraction of the elastic bands. This causes the wheel to rotate, right. So, we have a wheel, the spokes of the wheel are made of these elastic bands about a center of mass at the center. Okay. So, initially this wheel is at rest, the center of mass is aligned with the axis of rotation. Now, we attach a heat source. Okay. So, this is a heat source, this is our wheel, and these are our elastic bands. Okay. So, the rubber which is near to the heat source might change its composition, and based upon the type of polymer it might shrink or it might expand. However, any change in the length, either the contraction or expansion of the rubber, will cause a change in the center of mass or a shift in the center of mass of the wheel, which was initially perfectly balanced. Since the center of mass has shifted, the wheel will try to manage that, and it will rotate a bit. As soon as it will rotate, the rubber band that was exposed to heat will be exposed to the colder side or the cooler side, and therefore, those will again expand or contract in the other direction, and the new set of bands will be again exposed to heat. In this way, the wheel will be under continuous rotation. The wheel is not rotating on its own. We have a thermal input that is driving the wheel to rotate, and therefore, a thermal stimulus is giving a mechanical response. Such a system comes under this category of a thermoelastic or a thermomechanical system. Okay. And this mechanism of thermoelasticity is used in devices like micro electromechanical systems or nano electromechanical systems for causing motions like pull, push, right, or to perform some kind of work, bend, slide, etc. Right. So, these smaller structures you can provide inputs or of heat, small bursts of heat, and heating can be done through an electrical contact via ohmic resistance. We have not gone into the electromechanical systems yet. However, electric heating is one of the most common ways of heating. So, you can provide small inputs of heat, and that heat would cause a mechanical deformation. That deformation is our output and can be used for certain aspects, right. Okay. Now, we will talk about two phenomena. One is called the thermoelastic dampening and thermal stresses. So, two we can say mechanical responses that dampen or weaken a thermomechanical system right. So, these are the two processes or two phenomena that work against this process of a thermal input converting into a mechanical output, and that is a thermoelastic dampening and thermal stresses. So, what they are? So, the first one, that is your thermoelastic dampening. Okay. So, when a surface is impacted by a pulse load, what I mean by a pulse load is that you hammer onto a metal surface, that is a shock load or a pulse load. The elastic waves are generated, right, and this comes from the Navier's equation. So, Navier's equation we see is a wave equation. If you go back a couple of lectures, we will go into a solid mechanics where we have derived the Navier's equation in depth, and we can see that the equation del square u by del t square equals to some mu del square u by del x square is a wave equation, and that wave equation means that these elastic waves would propagate through the body. So, as the elastic waves are generated, they propagate through the body and reflect at the edges. Okay. So, if I strike it at one end, then the waves are generated from this point and they will propagate throughout, and it will strike the end and it will reflect back. Likewise, it will strike the other and it will reflect back in. Okay. The reflected waves may collide with each other and get dissipated in the form of heat. Okay. So, the colliding waves they can be dissonant, they can be out of phase, and that is the peak of one can match with the trough of another, and they may cancel each other out, and the energy that is within the wave is getting dissipated in the form of heat. Right. So, this heat energy is causes a local rise in temperature of the body, and due to the surrounding convection, it will get dissipated out, and therefore, the body will eventually cool down. However, that energy, that mechanical energy that you input into the body is getting lost or is getting dissipated in the form of thermal energy. So, the mechanical energy is thereby lost as thermal dissipation. This is called thermoelastic dampening. So, it is one of the ways in which energy can be dissipated and can be lost and may not be used for something that is useful or as a useful response. The second type of dampening or degradation phenomena will be a thermal stress. That is strains inculcated in a body, or rather strain induced might be a better term, during solidification or cooling, and due to thermal gradient causes stress generation. That is, if you have manufactured a body, that is initially it is molten and you have cast it and it is cooling down, or you have machined the body and locally the temperatures have increased, there is thermal gradient because surface is dissipating heat quicker than the bulk. So, there is a temperature difference. This temperature difference causes strains within the body, that is some part would have expanded more compared to another. As everything would cool down to room temperature and under a constrained atmosphere or conditions due to the mechanical constraints, that is the surface is held together due to some reason, and due to the lack of free movement of the surface, these thermal gradients would induce localized strains within the body. These localized strains translate in the form of stresses, and these stresses are called thermal stresses. These stresses are a major location of crack formation and dislocation growth, and when we impact the body or when we hit the body is under load. These localized strains or stresses they get magnified, and the magnification of these cause a fracture to propagate through. Okay. So, the thermal stresses get amplified under load and may be the hot spots of crack growth. Okay. So, these become the hot spot for the fracture to propagate or for the crack to grow. Okay. So, these are the two you can say the dampening responses of a body. This is natural, it will be there in any mechanical system. There are ways to mitigate thermal stresses is if you allow a more uniform cooling, a slower rate of cooling, that is annealing compared to hardening, right. If for those who study manufacturing sciences, if you cool down a body very gradually, then it does not develop thermal stresses and it remains more ductile compared to a body which is very rapidly dropped into a quenching medium, and it is hardened in that regards. So, it becomes hard and brittle because of the development of internal stresses, and those stresses becomes the point of crack growth, and the body eventually fails. Right. So, apart from these two, thermoelastic processes can be used to get a mechanical response from a thermal input, and we will look at 6 examples of such thermomechanical devices. Okay. The first one is our thermopneumatic systems. Okay. So, in these devices a gas couples the thermal source to the mechanical response. Or deformation. Okay. So, the heating is not directly done on the body, or the heating does not directly cause the body to deflect or to deform. There is an intermediate gas or fluid which is causing or which is taking that effect of the heat to the material that is getting deformed. So, that is a thermopneumatic device. Okay. So, typically resistive heating is used. To expand a gas. So, the gas heats up, its temperature increases, its pressure will increase, it will try to expand, its volume will increase. Now, if it wants to increase in volume, but you constrained it or you limit it, then it will exert a pressure, and that pressure translates to mechanical deformation. So, the expanding gas will exert a pressure on a membrane / plate, which will deform. Okay, so, that is the basic idea behind thermopneumatics. Unlike thermoelastics, which will have a direct deformation under a temperature gradient, in this case heat is translated through a media to the body. Okay. Let us take an example. So, one of the example can be a peristaltic pump. So, a peristaltic pump, if I draw it in a very rude, it is a very crude diagram. So, we have these small membrane pumps at the bottom. So, we have our flow through this tube. So, this is a tube. We have this small actuating device. So, these are some small actuating devices. What they have is that the bottom plate is a resistive heater. So, these are resistive heater. This is filled with a gas, and the top part is a membrane. Okay. So, what we are doing is we are actuating the heaters at each location. So, the first one is heated first, that will cause the gas to expand and the membrane to deflect. As the membrane would deflect, it will cause a local shrinkage in the area, and that will drive the fluid forward. Then the first one is relaxed, and the pulse of electricity is put into the second one. The resistive heater expands the gas, and the membrane will deflect, that will push the fluid forward. And in this way, if you can control or if you can actuate the electrical pulses, that will actuate the flow, and the flow will occur through this pump, right. So, that is an example of a peristaltic pump. Another example can be a micro bellow. So, a micro bellow device is this small segment of this actuating device. So, what they are that they have a membrane on the top, and they have a heater at the bottom, and this is filled with gas. They have a resistive heater, they have a membrane on the top. So, this membrane is going to deflect as the gas would expand, and as the this actuation of this membrane can be used for some mechanical response, for example, in the peristaltic pump. So, we can put in small micro bellows at the peristaltic pump, and that will regulate the flow, right. Likewise, it can be used for other applications, where this deflection on and off of these membranes can be used for certain actuating purpose, right. Okay. The second one, the second kind of device is a thermoelastic device. Now, this is what we typically would understand by thermoelasticity or thermomechanical response. So, in this case, the material deforms under the influence of a thermal gradient. So, you can say that we have a some form of a cantilever. You are giving some heat from here, some heat input that is causing a T hot and a T cold. This gradient would cause the cantilever to expand and to deform, and that deformation is used as an actuating purpose. So, the deformation is used to actuate a mechanical response. Okay. So, this is a very simple example of a thermoelastic device. You are giving some heat directly to the device that is causing it to expand due to its thermal expansion coefficient, and based upon thermal expansion coefficient we will get some strain. That strain or that mechanical response can be used to actuate. Okay. And the third one is a V-beam actuator. So, thermoelastic. Now, we are going into the domain of thermoelastic systems. Again, in this device what we have is we have two rigid plates at the two ends, and we have a structure this connected onto a rod that is giving us the mechanical response. Okay. Now, what we are doing, we are giving electrical inputs to both the ends. Which means that both these fixed ends, these are fixed ends, are heaters. They are heating elements and they are at a higher temperature T hot. This central part is at a lower temperature T cold, and it is getting a force as an output in this direction. Okay. So, we are getting an actuation in this V beam, this membrane or this elastic material. So, this is an elastic material. It can be made of any kind of alloy, it can be a polymer, based upon our objective is to optimize based upon the thermal expansion coefficient. So, as you have a thermal gradient between the cold and the hot side, this V beam is going to squish, and as the V beam will squish, it will push the rod forward, and you will get a mechanical response out from an electrical input or from a thermal input, rather in this case a thermal input. All right, that is a V beam actuator. Then the fourth one, we have a thermal bimorph. Actuator. So, a thermal bimorph actuator is something that is more predominantly used compared to a V beam actuator. It looks something like this. So, you have a thin rod and you have a thick rod. Okay. You have put a voltage input at the two ends. So, this is say at voltage positive, this is at voltage negative, means you are flowing the current through this. Now, a thin rod with a smaller cross section will be at will have a higher resistance compared to a thick rod. So, this is at a higher resistance, this is at a lower resistance, that is electrical resistance, R electric. Therefore, the thin rod will be hotter, the thick rod will be colder, and this temperature differential will cause this actuator, that is the bimorph actuator, to deform or to deflect, and that deflection is typically used for some MEMS response or for some MEMS actuation. Okay. So, the current is flown passed through the bimorph, right. The thinner arm gets heated more than the thicker arm, due to higher electrical resistance. The thermal gradient will cause a mechanical response or a mechanical deformation in the thinner arm. So, the thicker arm will also deflect or it will also bend, but the thicker arm is made in such a way that the temperature does not vary that significantly. It is thick enough that the heat generation is low. If the heat generation is low, it will be able to dissipate heat very quickly and the temperature does not change too much. The thinner arm is where the temperature will fluctuate significantly, it will rise a lot, and therefore, you will have the fixed lower arm, the upper arm is going to bend up or bend outwards, and you will see a deflection. Okay, that is a thermal bimorph. Then the last two, we have a bimetallic actuator, which is the most commonly used structure. Many of you might have seen these kinds of actuators in those clicking switches, right, or fuses, that if you put in current, the switch will bend and will get out of contact as the temperature exceeds a certain value, right. So, you have these thermal switches. So, if the temperature exceeds a certain value, it will flick off or it will kick off from the contact, and the contact will open, and therefore, the circuit is disconnected. As it will cool down, it will come back to the original position and the contact will be maintained. Okay. So, it has two strips of similar geometry, but different materials. By materials, we mean different thermal conductivities or thermal expansion coefficients. Right. So, we can take, say, a cantilever, which is having two materials more or less a similar geometry. You can take different geometries as well, but different geometries are more similar to this bimorph structure, which has the same material, but different geometries. In a bimetallic actuator, you have two materials. So, you have an alpha 1 and alpha 2, more or less a similar geometry. Now, if you put a thermal gradient, will cause one strip to expand more compared to another, thus causing the structure to bend or deflect. And this is the kind of response we look. For example, if alpha 1 is greater than alpha 2, then the top would like to deflect or displace more compared to the bottom, and is likely to bend downwards. So, if you have say this is the bimetallic and it is divided into two halves, and you have an electrical contact like this, due to thermal difference, the top will like to bend more and it will deflect downwards, and the contact is cut off. When it will cool down, it will come back to contact. So, we can have a thermal switch like this, which can cut off when a certain temperature is reached, and it will remove from the contact, and once it is cooled down, it will go back into the contact. And that is the beauty of a bimetallic actuator, a bimetallic strip. The last one is quite interesting. It is called a shape memory alloy. So, what is a shape memory alloy? That unlike a bimetallic strip in which thus the material expands and contracts, these materials, or this class of materials undergo a phase transformation in response to a temperature change. So, due to a temperature change, it will undergo a phase transformation, which, for example, steel can go from austenite to martensite, and these phase transformations can make the materials from less ductile to more ductile, and therefore, you can train the material to a certain shape or to take up a certain shape. Change. It can be trained to return to a specific shape based on the temperature. So, these materials will likewise can be trained to attain a certain shape at a given temperature. Okay. Now, with this introduction, we know that there are several applications of this thermomechanical devices, and it is something that you can practically use in some sort of an engineering application, in a control system or the development of a larger equipment. Right. So, we will start with the modeling or the development of a model for a thermo-pneumatic system. We will start with a very simple case of a mass spring system, and we will gradually move on to more complex systems. Okay. So, a mass spring system, we can consider a piston cylinder assembly. Filled with a gas, the piston is connected to the bottom wall by a spring. Okay. So, let us draw this geometry out. So, you have this piston at the top, the solid piston, it is rigid. The bottom plate and this piston is connected through a spring to the bottom plate and it is filled with a gas. The spring has a spring constant of small k. This is your piston and this is your cylinder. So, this piston can move based upon the expansion of the gas. It will most likely be going up as the gas is expanding. The bottom wall of the cylinder is a resistive heater which will heat the gas. As the gas expands, the piston is displaced outwards. Okay. So, the piston will move up as the gas would expand. So, the bottom wall is a resistive heater. The gas couples the piston's movement with the heating input. Okay. So, let us so we are solving for two kinds of equation. One is the equation of motion. In this case, we have a spring mass system, and second is the thermodynamics, that is a thermal system. Okay. So, let us first start with our piston, that is the equation of motion. So, we can say that the volume of the piston displaced V as a function of time will be equals to area, that is constant, that is the area of this cross sectional area of this. The initial length L, some initial length L, say that it is initially at L, plus x, that is your displacement. So, it has gone to this location, x as a function of time t. So, this is the volume change, this is the volume, net volume at a given time t. Initially, it is A into L, that is your V at time t is equals to 0, and as the piston would expand, your volume would change. Okay. Assume that the gas is ideal. So, we can say that P V is equals to N R T, where N is the number of moles, R is the gas constant, universal gas constant, T is the temperature, P is the pressure, and V is the volume. Okay. Now, by Newton's second law of motion, we can say that the mass times acceleration is a summation of all the forces. Now, what kind of forces are acting? We have a spring that is pulling it back, that is minus k x, a small k, and we have a pressure that is pushing it upwards, that is P into A. We are not writing it vectorized because we have declared it is a one dimensional system, the piston is only moving up and down. Okay. So, this is our equation of motion. We need to couple this pressure with temperature, and we can use our ideal gas law. So, we can say that pressure is equals to nRT over volume V. Therefore, m d square x by dt square will be equals to minus k into x plus nRT into area over volume V. We can replace volume as A L plus x, and therefore, it is equals to, and we can rewrite this equation again, m d square x by dt square is equals to minus k x plus nRT over L plus x. This is our equation of motion. This is our first equation. Of course, we need boundary conditions for this. We can say that at x is equals to 0, our the length is L. So, x of 0 at time 0 is equals to 0. It is not displaced and it is at L. Okay, so, this becomes our initial condition of motion. Okay, so, this becomes our first equation, our displacement equation. Then we go into our thermal equation. So, the thermal equation will be our equation of T related to x. So, again let us see that from this equation of motion we are relating x to T. In the second equation, likewise the T, that is the temperature, is also dependent on x of T. So, it is dependent on the position and time, okay, and we need to derive an equation for this. So, for that, since we are using an ideal gas for expansion, we can consider that that the first law of the system is applicable, and we can apply the first law for this kind of analysis. So, from first law of thermodynamics, we have internal energy is equals to change in internal energy is equals to change in heat plus change in work done. This is our first law. If we integrate from two states, say the initial state is at time t and the second state is time t plus dt. From t to t plus dt, that is t is state 1 and t plus dt is state 2. We will integration of t plus dt of du is equals to integration of t plus dt dq dw. Okay. Now, we need to find out each of these, this del q and dq and dw. So, for dq we know that the energy that is being put in is lost in terms of convection to the surrounding. So, the heat is convected. I am sorry, the heat being generated by the plate is being transferred into the gas via convection. I was thinking of a different problem. So, say that the hot plate is at a temperature Th and the gas initially is at a given temperature T, say Tc, and as the plate is heated up, or as the hot plate gets in contact with the gas gets in contact with the hot plate, then the heat is transferred from the hot plate to the gas and the gas gets heated up. So, we can say that dq by dt therefore equals to minus h into a T minus Th. Okay. From the work done equation, and now this gas is getting heated up and is going to expand and do some work. So, there is some pressure and there is some change in volume. So, we can say the work done by the gas due to expansion, right, that is dw by dt is equals to minus p into dV by dt. So, pressure is a function of time into dV by dt, right. Okay. So, if both of them are there, then we can say this equation we can differentiate with respect to t, and what we will get is du by dt is equals to dq by dt plus dw by dt. Therefore, our internal energy change energy rate we can write as du by dt is therefore equals to minus H A T minus T hot minus P into dV by dt. Okay. Now, we can try to relate this somehow to our displacement. First of all, we need to know what u is for an ideal gas. U is equals to K, capital K into nRT, where it is a dimensionless constant. Okay, and depends on the degree of freedom. For a monoatomic gas, it is 3 by 2, for diatomic gas, it is 5 by 2, and so on, right. That is the value of K. So, we can substitute this in this equation, and we can say that K N R dt by dt plus H A T minus T H equals to minus P to dV by dt. We can substitute this P from our gas law, and that is minus N R T over V into dV by dt. We can write V as area into L plus X. So, minus N R T area into L plus X, and this becomes dx by dt. Okay, and the area comes out. The areas will get cancelled, and therefore, our heat transfer equation will become K N R dt by dt plus H A T minus T H will be equals to minus N R T over L plus X into dx by dt. This becomes our equation 2. We also know the initial condition for this will be the temperature at 0 is equals to some initial temperature T 0. Okay, that is our initial condition for our heat transfer equation. Now, if you see that our heat transfer equation or our thermal transport equation, that is that temperature changing with time, is dependent not only on time, but also depends upon the spatial x, that is the displacement, and our displacement equation 1 dependent upon not only on time, but on temperature as well. So, this is called a two-way coupled equation, where equation 1 depends upon the variable of 2 and equation 2 depends upon the variable of equation 1. Okay. Now, what we can do is that we have a lot of constants, this capital K N R, then H A, we have the spring mass, spring constant, the piston mass, the spring constant. All of these we can club them into some dimensionless constants, and that is the role of non-dimensionalization. So, we can do a non-dimensionalization. So, non-dimensionalization of this equation, we can say that theta is T minus T hot over T hot. Our time normalized is square root K over M of T, and our U will be X over L. Now, let us take our first equation. Let us see what our first equation was. M d square x by dt square minus k x equals to nRT over L x. Let us check one more time. Yes, that is correct. Now, we can substitute. So, this was our governing equation 1. We can now substitute our x and our times and our temperature in this case. So, it will be m L by k by k over m. I am not writing it correct. It will be m over k. Sorry, let me write it correctly. Okay, m over k into d square u hat by t hat square plus k into L u hat will be equals to n r. Now, T we can write as theta into th plus th, that is theta hat plus 1 into th divided by we have this L plus x term. So, that is L 1 plus u hat. So, x becomes u hat into L, L you can take out common. All right. Now, let us remove this m. We can divide our equation by k into L, and what we will get is, so divide by KL, okay. And what we will get from here, we will get the first term is d square u hat by dt hat square plus u hat will be equals to some alpha into 1 plus theta hat by 1 plus u hat. Okay. So, the objective, if you go back to our former slides on this dimension analysis and non-dimensionalization, we will find that we divide the constant that we are getting in terms of the highest order derivative throughout. So, our highest order derivative constant is KL, you divide everything with KL. What is alpha? The alpha that you will get, alpha will be equals to NR into T hot divided by small k into L square. Okay. So, this is in some respect it is a ratio of your pressure force to your spring force. Now, how is this pressure force? NRTH, if you multiply and divide by volume, then this will be pH, and you have multiplied and divided by volume. So, you will multiply volume over here, volume is A into L, that is the initial volume, over K L square. So, this L will get cancelled out, and it comes out to be pH into A over K into L. This is our initial spring force. pH is the pressure when the gas is at TH. So, when the gas is at TH and has expanded to TH, that is the pressure of the gas, right. So, this becomes our equation. Let us say this is equation 3. Likewise, equation 2 can be normalized, and the equation that we will get is d theta hat by dt hat plus beta into theta hat equals to minus 1 by capital K 1 plus theta hat by 1 plus u hat into du hat by dt hat. All right. Here beta is equals to square root m by k over capital K n r over h into a. What is this? This is the oscillation time scale to the thermal transport time scale. Okay. So, these non-dimensional constants are extremely useful. They give us information of whether we can keep a term or we can reject a term. Okay. Now, to solve this type of equation, we can take two approaches. One will be a set of analytical approach. So, an analytical approach for this, now this is a coupled equation, you cannot fully solve this analytically, it will be very difficult to solve. So, analytical approach you will need to do some simplification. We take at steady state, we take theta hat equals to 0, theta hat will be 0 when temperature will be equals to TH, means that the gas has reached steady state and has become at TH, that is T is equals to TH. Under that condition, if you look at our first equation, then this is equation number 4. The first equation, this is 0, u hat will be equals to alpha over 1 plus u hat. So, from equation 3 will be equals to alpha over 1 plus u hat. So, this becomes our equation. Therefore, u hat square plus u hat minus alpha equals to 0. This is our equation. what we can get as an output is u hat equals to minus 1 by 2 plus minus 1 by 2 square root 1 plus 4 alpha, right. Now, u hat we know is is x over L. If we take the negative counterpart, for the negative counterpart, then u hat will be less than minus 1. That means that the plate has the piston plate has crossed the bottom wall, right. So, the piston plate has crossed the bottom wall, and that is not possible, right. It cannot break through the resistive heater. So, that case is rejected. We can only take the positive case. Therefore, u hat equals to minus 1 by 2 plus 1 half of square root 1 plus 4 alpha, and this is our solution. Now, if alpha is very small or alpha tends to 0, that is our pressure force is very small compared to the spring force. In that case, we can say that we can linearize this expression. We can linearize our equation. So, linearize our equation, and we can get that u hat will be proportional to alpha into L, which is proportional to pH. The alpha is pH into A by KL. So, pH into A over K. Okay. Which we can say that the pressure force is balanced by the spring force, and the equilibrium distance is this u hat. Okay. So, into L, that is u hat into L, that is x. Okay. So, this is the equilibrium distance of x at which the pressure force balances out with the spring force. Now, again this process can be done numerically. So, numerically is you can solve the entire equation. So, if you look at equation 3, I will just write down one, and the second one you can try yourself. So, del square u by del t square plus u hat equals to alpha into 1 plus u hat by 1 plus theta hat. So, this is a second order time derivative. What you can do is you can discretize this equation of u hat of I plus 2 minus u hat of I plus 1 2 times plus u hat of I, or if you want to do a centrally differenced, then minus 1 and 1 divide by dt square plus u hat of I equals to alpha of 1 plus u hat of I by 1 plus theta hat of I. Now, we do not know what this u theta hat of I is. So, in that case we can take a guess value of theta hat of I, and we can iterate over this. Likewise, you can set up a similar equation for the theta hat condition. This du by dt, and it will be ui minus 1 by delta t. So, numerically this problem can be solved. In the next lecture, I will show you an output plot of how this looks, considering some values of alpha and beta, and then we will move on to a membrane based problems. From that, we will finish off the thermomechanical model considering a thermoelastic system, and take that up, try to solve this problem analytically and numerically, and finish thermomechanical problem. So, thank you for listening today.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.